Welcome to my talk. Today I will give a talk about our work, query-directed adaptive heap cloning for optimizing compilers. It is well known that point-of-alias analysis has been used extensively in modern compilers. And in point analysis, we need a heap model to model how heap objects are analyzed. Heap cloning aims to statically distinguish heap objects by call paths. Let me use a tiny example to demonstrate what heap cloning is. There's two methods. In the first method, man contain there's a two buffer allocated via method getMap. In dynamic execution, we know that getMap will be invoked twice, and these two buffers definitely point to two different heap locations. However, in static analysis or analysis during compile time, we always do approximations. In one extreme, we could assume these two pointers, buffer 1, buffer 2, point to the same heap abstraction created at the location site. This analysis is fast but not precise, because these two buffers should refer to two different heap abstractions. However, your approximation is too conservative. In another extreme, two new heap abstractions are created at each call site according to call paths. In such way, the precision is improved because two pointers are distinguished by pointing to different heap abstractions. We call this kind of analysis heap cloning or context-sensitive heap cloning. It seems very easy for us to perform heap cloning on this tiny example. However, in real program, the case might be too complex that more than we can imagine. We can see that this is part of call graph or program TCC, that there's too many calling relation and call paths. It is very costly to perform heap cloning everywhere across the program. To tackle this problem, many previous work use k-context-sensitive heap cloning techniques. Actually, this technique is a trade-off between analysis efficiency and precision. K here is the tunable parameter, indicates the last k call path in the acyclic call graph. Let me use a simplified call graph to demonstrate the basic idea of k-context-sensitive heap cloning. We could see that this is a call graph, and the rounded corner rectangle stands for procedure, and the edge between them represents the calling relation. We could see that there is a black node at the bottom of the call graph is created at the location site. This means a heap object. And if k equals 0, it means we do not perform any heap cloning. And in fact, this is most imprecise analysis, which means if this heap object return to its callers and pass to pointers, all these pointers receive this heap object are assumed to be point to the same heap objects. However, if we look one level high, there's two procedures. Each procedure may contain multiple call sites. In each call site, heap cloning is performed. That's the reason why there is more than one heap node created inside one procedure. In such way, the precision is improved. We can even see that these three heap objects on the left can only be pointed by the pointers along the call path, along the two call paths on the right, and the two heap objects on the right can only be pointed by pointers through that call path. And similarly, if we increase the k to equals 2, and more heap nodes are cloned, and then eventually we will reach top end of the call graph and perform full heap cloning. Ideally, full heap cloning has the best precision. However, it may be too costly to be applied in large and heap-intensive program. For example, we can see this bar graph shows the analysis time of program GCC with Anderson-style context-sensitive heap cloning. We can see that full heap cloning is 14 times slower than context-sensitive analysis without heap cloning, and 22 times slower than OpenSix4 compilation time under minus O2 option. Okay, give all these observations, it's time for us to rethink a heap cloning problem. That full heap cloning really matters, that according to a class requirement, do we need to perform full heap cloning everywhere across the program? If not, is k-cos sensitive heap cloning with a fixed k the best solution? In order to answer these two questions, we need a client. Of course, compiler stop is the best client for us to use because they have modern compiler have many optimization and transformation phases. Most of these phases need alias information in terms of alias query. What is alias query? Alias query contains a pair of expressions to be asked whether they may represent the same memory location or not. Remember that we have buffer 1 and buffer 2. This query counts to ask whether they dereference the alias or not. If they do not perform heap cloning, the query are not answered positively. They may reference the same memory location. However, if we perform further cloning, we can see previous example that they are distinguished, so the query are answered positively. And here is graph shows the alias query generated from warped module from Open64. And warped module actually contains most of machine-independent optimization and transformation phases. This graph gives us sense where these queries are coming from. And we could see that nearly 500,000 queries are generated from warped modular in Open64 across 15 spec to 1,000 safe benchmarks. And given all these queries, it is sufficient enough for us to measure our heap cloning analysis. Let us see the alias query result of 4 repetitive programs when different level of heap cloning is applied. We could see that the horizontal axis means k-cos sensitive heap cloning, and the vertical axis means must not query answer. The higher the better. The higher the more precise. We could first say that on the left-hand side there's 2 programs. The precision grows steadily when k increases. And we could see there's bottleneck here. And there's not much precision improvement when k equals 3 or greater than 3. One typical example is 2 errors. We can see that only one cos-sensitive heap cloning is enough. There's no precision improvement after the further heap cloning. And for some example, like vertex, we can see that biggest precision improvement happens when k equals 3 or greater than 3. Let us take a picture to discover the reason behind. Here is the code graph of this program. Actually, this is a database program. If you want to create a database, you have to create trees. And finally, if you want to create trees, you have to create arrays and a different attribute array. And finally, at the bottom of the code graph, there is a location site. And clearly, we can see that if we do not perform three cos-sensitive heap cloning, there's not much precision benefit there. Because after the third steps of code graph, we can see there's many callers and call set there. And after all this observation, we can see that full heap cloning sometimes is unnecessary, and full heap cloning is over cloning. It's always over cloning. And k-cos sensitive analysis with a fixed k also has problem because different programs have different behaviors. Therefore, you cannot pick a fixed k to satisfy all the programs. Our goal is to enable heap cloning only where it is necessary and achieve the same precision as full heap cloning. Here is our QDA framework, query-directed adaptive heap cloning. What's the novelty? The novelty is that we perform k-cos sensitive heap cloning iteratively. And we start with context-sensitive analysis without heap cloning, and heap abstraction is cloned at the next iteration if and only if the alias query are not answered positively at the current iteration. As the name implies, query directed means we only perform heap cloning where it is necessary, according to alias queries. And adaptivity means during each iteration, only heap-related part of program can be further cloned, while the rest part of program remain unchanged. Before I introduce technical details, let me show a graph and example to demonstrate the basic idea and intuition. Here is a code graph we have seen before, and we start with content-sensitive analysis without heap cloning, k equals 0, and then we feed our quantity information into compiler to issue queries, and suddenly a query coming from this method to ask whether the reference P and Q are alias or not. In the first scenario, they must not alias, which means we are done. We do not need to perform further heap cloning. The precision is good enough, even k equals 0. And in the second scenario is that they may alias. They may represent the same memory location. There are two cases. In the first case is that they're not heap related, which means they may initialize to be pointed to the stack of global variable. In such way, we do not need to perform heap cloning either, because even if we perform further heap cloning cannot improve the precision. In the second case is that they are heap related. For example, there is this heap node return to its caller and pass its value to both P and Q. Then they are heap related and may alias. In conventional heap analysis, a heap model is fixed, which means even a query is not answered positively, and the result still cannot be changed. And in our heap cloning, in our analysis, we perform another round of heap cloning to clone heap nodes inside the caller procedure. And then we feed our new points of information to the compiler backend for issuing this query. If we are lucky enough, which means if there's two different heap abstractions returned to its callers and pass to P and Q through different call paths respectively, and they are distinguished. So we are done. We do not need to perform further heap cloning. However, sometimes we're not lucky. For example, this heap object is passed to its returned to its caller and passed to the same call path and pass value to both P and Q, so they cannot be distinguished. However, we only need to perform further heap cloning about this heap object, because according guided by the query, the other part of the program remain unchanged. So we perform another round of heap cloning. What's the worst case scenario? The worst case scenario is we keep performing heap cloning until reach the top end of the call graph. So we are done. Okay. Next, I will introduce some technical details and tiny example quickly. And we start from heap-where point solver. Our heap-where analysis builds on top of existing subsite Anton-style point analysis by adding the gas into each point relation to specify which heap object might be further cloned to improve precision. Here's two simple point relation. X points to a stack of global variable G, and the pointer P points to a heap object. In traditional or conventional heap analysis, these 2 points relation are not distinguished. However, in our analysis, we adding the gas into each point relation to distinguish them. For example, in the first point relation, we add true, which means this point relation is always whole during any iteration. And then add HO into the second point relation to indicate that this point relation might be spurious if O is further cloned. This is trivial. So how we perform to get the heap related information during point resolution? For example, we have a store and log X and Y store X store to P and Y log Q to Y. Remember that P and Q, if they have a less precise heap model, they may point to same heap object O. And in such way, X value can pass through these layers into Y. And finally, Y gets points to target G under condition HO. Let us see how we can further clone to improve the precision adaptively. Then the query comes, asks whether the reference X and Y are alias or not. And then we pick the candidate heap object for the improve it. Definitely we know that they are alias. We pick this O and add into candidate side. Then we perform adaptive update. There are several implementation choices. One choice, you can still keep the old O on the graph and use the next level heap information to easily increase. And another choice is you just remove O from the graph. And then for next round, heap cloning and P and Q are distinguished. In such way, X value cannot flow to Y. So the query are answered positively. Okay, let's move to our implementation. Our QDAF framework is implemented in Open64 compiler. And our heap awareness is implementing IPA module. And without loss of generality, we use a summary-based analysis to perform context-sensitive analysis. It has two phases, interleaves until a fixed point is reached. And then we feed our points information into warped modular for easy increase. And at the same time, we write our construct graph into ELF files and then read it back when the query result comes. And finally, we perform adaptive update before the next iteration. The total analysis time includes the modular following the right arrow. And at this stage, we want to test our scalability and feasibility. We also include the analysis time passing through the warped modular. Even in this case, our adaptive heap cloning is significant faster than exhaustive heap cloning. We could see that this analysis time compared with Focal and CUDA. Focal is a state-of-the-art context-sensitive heap cloning. And we could see that in average, our CUDA framework only costs 75% of the total compilation time, while Focal is 7 times slower than Open64 compile time and -02. For the large benchmark, we are even better. Okay, here is the heap objects reduced by CUDA or Focal. We could see that 70%, around 70% of heap objects are reduced. Let me show you a real example picture generated by our tool, by comparing with full heap cloning and CUDA. Let's see this graph. Here's a core graph. The white nodes represent each node represents procedure. The white nodes means the procedure does not contain any heap object. And the blue color procedure means this procedure contains at least one heap node. And the light green color procedure means this is a heap intensive procedure. It contains heap nodes more than 50. We can see this comparison clearly that we reduce, there's a fewer procedure contain heap nodes, and we only perform heap cloning where it is necessary. Okay, here is the alias query to be answered at each iteration. We can see that first, alias query to be answered, which means alias query is answered in 3 cases. The first case is that they are must not alias. And next is they are not heap related. The third case is they cannot be further cloned in the core graph. We can see that in the following iteration, fewer and fewer queries needs to be answered. And there are several special cases here. We can see that like vortex, rasta, their query can only be answered. Their query can only be answered when k equals after equals to a third iteration. And here is the analysis time per iteration over the total. We can see that after the first iteration, in the following iteration, they contain a relatively small percentage over the total. That is because only heap-related part of the program needs to be adaptively updated, guided by the query, and the other parts of the program remain unchanged. And here are some special cases here, like MISA and Perl. They are quite heap-intensive program and requires a relatively higher percentage of total analysis time during the following iteration. However, it still remains a reasonable range. Okay, finally, let us move to the conclusion session. Our work proposed a novel heap cloning approach. Achieve the same precision as full heap cloning and guided by the alias queries. Here is some, in general, our idea can also be used in some other research area, like iterative compilation, to let them converge, to help them converge more quickly, or some adaptive bug detection to scale their analysis. Okay, thanks.
Time for a few questions.
Hi, Phil Miller from the University of Illinois. Could you possibly reduce the number of objects? Could you possibly reduce the number of objects that you have to clone the heap further by doing, I guess, a pre-pass through the analysis, up through the call stack, indicating functions that always return new heap objects to flatten out some of that context step?
Yes, because if you do not consider context-sensitive analysis, heap cloning actually is useless. So when you perform heap cloning, you have to distinguish different calling contexts. So in such way, the pointer can point to different heap abstractions.
No, I'm suggesting an inlining kind of.
Inlining. Inlining is very costly, especially for large heap-intensive program. For example, if you at the bottom core graph, you can see. Let us see. Of course, inlining is a very simple way for us to perform.
I'll explain what I mean offline. I'll talk later.
Okay.
Maybe one more question. I had a quick one. So you were basically going up in a call graph level by level.
Yes.
Would it be possible to augment the call graph with additional information to see if it's sufficient to just go up at certain branches?
Okay, it's a good question. Yeah, actually, our work actually opened up an opportunity for the adaptive analysis, for point analysis. And actually, this many optimization choice and Frank mentioned. This is a definitely interesting future work we can do. Yeah.
All right, let's thank the speaker again.